Okay, so we're almost done with chapter 9, and then we're going to get into the glorious chapter 10, where we talk about the equations of stellar structure. Such wonderful stuff. Where is my chalk thing? In here, I think. Oh no, where did I put it? Okay, anybody see where I laid my chalk holder? Oh, yes, I think it's my laptop case. I'm so silly. Okay, there it is. Ah, glorious. Because I don't want to get my hands all dry like I did one year. Just so much chalk dust and everything. Okay, so we're going to finish up on spectral lines here. And finally explain why there's kind of two main sequences, luminosity class 5, luminosity class 6. So I will remind you that we were talking about pressure and collisional broadening, and that we found that the full width at half max is equal to lambda squared over pi c times 1 over delta T naught, which is about lambda squared over pi c times n sigma. N is number density, number of particles per cubic meter. Sigma is not the Stefan Boltzmann constant, it's the cross section, remember, for interactions. Square root of kt divided by m, and the point here is that the line width depends on the number density, because there it is. Wow. Come on, Hagoromo. I can probably continue to use this a little bit. Okay. Depends on the number density. Maybe it's just I'm too enthusiastic and I'm just pressing too hard. I must be gentle, gentle. There we go. Is this okay, Kathleen? Can you read that? I was trying to be gentle with the chalk. Maybe that's too gentle. Okay, okay. Depends on the number density, which, you know, think back to what we were talking about. Collisional broadening, pressure broadening is when atoms either smack into one another or have close encounters with one another. So higher number densities means that happens more often. It's a bigger effect, more broadening. And so the higher the number, the higher the number density, the broader the lines will be. And what was that? Oh, was that sharpening a pencil? Is that what that was?
Yeah.
Oh, okay. I was like, we have a robot or something in here, right? Okay, cool. All right, that's fine. I was just like, what is happening? Okay, depends on the number density. And this explains the narrower spectral lines of giants and supergiants compared to main sequence stars. That's why this happens. We talked about, we did talk about that before, right? The giants and supergiants have narrower spectral lines, right? So revisiting, here it is in detail why that happens. So this explains the narrower spectral lines seen as line widths, spectral line widths seen in giants and supergiants. Giants and supergiants. I will say, you know, just writing the words there, that I do like that we talk about giants and supergiants, you know, in astronomy for stars. Supergiants, what a great name, you know, for those stars. Seen in giants and supergiants. namely that the number density is low in a giant's distended atmosphere. So fewer close encounters, and so less broadening of the lines by the electric fields of nearby atoms or by shortening the lifetimes of states by collisions. The number density is low in a giant, supergiant, or supergiant's distended atmosphere. I'll do the thing where you say, parentheses, supergiants, where that means giant or supergiant, distended atmosphere. And if you don't know what distended means, it means all big and bloated out, essentially. Okay, right, I was thinking, yeah, distended, right? New word of the day, distended, all spread out. Yes, maybe, although I'd prefer to extend it. Yes. I mean, kind of similar, but we would say extend one's knowledge, whereas if something gets kind of overgrown, it has become distended. So one's belly becomes distended, one's knowledge is extended. That's the sort of thing we're talking about here. Okay, let's see. So, subdwarfs luminosity class Roman numeral 6 have lower metal abundances. Because they are old, and so the interstellar medium was not so enriched when they were born. And so the ISM, which stands for interstellar medium, had not been very much enriched in metals when they were born. What's a metal? Is carbon a metal? Yes. Of course it is, yes. Who would ever doubt that carbon is a metal? And so the ISM had not been enriched much, I'll say, when they were born. So they don't have as much heavy elements, it has as much abundance of heavy elements. And I'll make a quickie sketch to remind you of the idea of, okay, here I am trying to be responsible. I'm going to regret this because it's all this chalk that's just going to, all right, but no, I'm going to do this. Okay, so remember that when we talked about the different luminosity classes, let's see, here's temperature going that way, here's luminosity going that way. What's that? Oh, please, 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 no. What's that big, long diagonal line on the HR diagram? That's the main sequence, right? That's the main sequence. And what luminosity class is that? 5. That's 5. Yeah, that's luminosity class 5. That's the main sequence. Those stars are getting their energy from the fusion of into in their hydrogen and helium in their cores, right? Yep. So are these stars. Kind of a parallel lower main sequence there. These are very old stars, and so the upper part of the main sequence is missing. The high mass stars live fast, die young. They blew up a long time ago, but the lower mass ones are still here. This is luminosity class 6, and those are low metallicity main sequence stars that typically live in the halo of the galaxy, in globular clusters or in the general halo that extends above and below the disk. So luminosity class 6 is low Z, right? We said that Z is the metallicity. Low Z main sequence stars. And it's tempting to think of luminosity class 6 as lying below the main sequence, and that's how it was originally thought of, I think, but it's better instead to think of it as being shifted to the left of the main sequence. So think of it as shifted to the left towards higher surface temperatures. And why would this happen? Well, now that we know something about opacity and optical depth, and you can quote unquote see to an optical depth of 2/3, why we've got all the ingredients we need in order to explain what these stars represent here. So because they have a smaller abundance of metals, low Z says the electron number density is lower because it's atoms that have more protons in the nucleus that have loosely bound electrons in their outer shells that are easily removed, easily ionized, and contribute to the number density of electrons in the atmosphere. So Ne is lower since metals are an important source of electrons via ionization. Since outer shell electrons are loosely bound. Right, I mean, think of, so in the sun's photosphere, which is really, we're talking about stars' photospheres, what's the most common type of atom in the sun's photosphere, or in any ordinary star's photosphere, or any ordinary star period? It's hydrogen for sure, right? At solar temperatures, are there many ionized hydrogen atoms, or do most of them still have their electrons? Well, if you say yes, you could be answering yes to either, right? So, I mean, you're not wrong. Yeah, right. Am I beautiful or ugly? Yes. Right. Okay. Good. Yeah.
What was the question?
In the sun, in its outer layers, where the photosphere, where we're getting the light, is most of the hydrogen ionized or neutral? Neutral. Definitely neutral, right? Goldilocks and the three stars. At what temperature does hydrogen start to become significantly ionized? Around 10,000 Kelvin. What's the sun's surface temperature? 5,770, which usually, yeah, and so the book's good. There's a 5770, but I'm here to tell you, usually astronomers say 5,800 Kelvin. That's a little easier to remember. So there's essentially very few free electrons in the sun's outer layers from hydrogen, and helium too holds on to its electrons even more tightly than hydrogen does, right? It takes 15,000 Kelvin to start ionizing helium. And so most of the free electrons in the sun's photosphere are from metals because they're easier to ionize because they have outer shell electrons that are loosely bound. So most of the electrons wandering around free in the sun's photosphere are due to metals. And remember that hydrogen has some electron affinity. It's able to attract and bind to a second electron. So in other words, it forms the H- ion. Lower Ne, lower number density of electrons, means less of the H- ion. And again, if it seems weird to you that there's H-, just think about if you dissolve salt. What's salt? What's salt made of? NaCl. Yeah, NaCl, right? Natrium chloride, right? Na comes from natrium, basically. But sodium is what's that? Yeah, natrium, so, but we say sodium, right? Natrium, I guess, but we say sodium. If you dissolve salt in water, then sodium chloride is an ionic solid. In other words, basically, sodium doesn't hold its outermost electron very tightly, and chlorine would like to, quote unquote, would like to have another electron to fill its outer shell. Now that's not really its goal, is filling the outer shell per se, but it translates into you can actually release some energy by binding an extra electron to a chlorine. And so when you dissolve salt, you get in the water positively charged sodium ions and negatively charged chlorine ions. This is chlorine with an extra electron bound to it, and that gives off energy. And this is the same thing. Hydrogen has some electron affinity. You can bind an electron, a second electron, to hydrogen. There's only one energy available to it. We mentioned that before. It's very loosely bound, and so infrared wavelengths, or anything shorter than like 1600 something nanometers, can strip it off, so that H-, you may recall, and if you don't, I hereby remind you, is the primary source of continuum opacity in sun-like stars. There's this H- ion with this loosely bound electron, and it's really easy to strip it off with any visible light photon. And so that's the primary source of continuum opacity. So there is a lower continuum opacity in those stars. In low metallicity stars, there's not as much H-, and so their atmospheres are more transparent. Their atmospheres are more transparent. It's got a lower opacity, same thing as saying it's more transparent. And in particular, so the level where tau equals 2/3, and I could put, well, I could put tau v on it if you like. The vertical opposite of F, we'll say, is 2/3. The tau v equals 2/3. If the atmosphere is more transparent, if it has a lower opacity, is that layer, is that level deeper below the top of the atmosphere or closer to the top of the atmosphere? Would the tau v equals 2/3 level be deeper down below the top of the atmosphere or higher up, closer to the top of the atmosphere, if the opacity is lower, if it's more transparent? Mm-hmm. So think of being in a fog, right? Because opacity describes a fog too. When can you see further? When it's foggier or less foggy? When it's less foggy, you can see further, right? So these atmospheres are less foggy, so to speak. They have lower opacity. They are clearer to see through. So you can see deeper into the star as a result of that. The tau equals 2/3 level is at a greater physical depth below the top of the atmosphere in these stars. And of course, remember, top of the atmosphere is a bit of a myth. It doesn't suddenly stop, but shh, you know what I mean. We just have to pick some level where we say, it's practically nothing above this. Well, deeper in, temperatures are higher, right? For a given nuclear reaction rate in the star, the luminosity is going to be the same, but if I can see deeper in, I'm seeing hotter, deeper layers. We see down to hotter, deeper layers. So, what does that say about the effective temperature that we're seeing? If you're seeing hotter, deeper layers, I mean, I'm practically giving it away. Does the star's surface look hotter or cooler if I can see down to hotter, deeper layers? Not a trick question. Why, it looks hotter as a result of this. Tef is higher for a given luminosity. Tef is higher for a given luminosity. Imagine that you suddenly made the sun's atmosphere more transparent. You'd see deeper into it, and it would look like the sun's radius shrank a bit. Even though it didn't, it would look like the sun was a little smaller because you were seeing deeper into it. And again, it's a fuzzball, right? But if you can see deeper into the fuzzball looks smaller. So it would give the sun an apparently smaller radius but higher surface temperature, such that 4 pi r squared sigma Tef to the fourth was still equal to the sun's current luminosity. So it would make the sun look smaller but hotter, such that it would still have its same luminosity as it does today. And I'll say so, and the radius is effectively smaller. Right? So I take a star of a given luminosity and I increase its effective surface temperature. That's precisely shifting it to the left a bit on the HR diagram. And that's what these stars represent. We can see deeper into them because they have less H minus, because they have lower metallicities. We can see deeper into them, and so they look a bit hotter than higher metallicity stars of the same luminosity would. So luminosity class 6 is shifted over a little bit. If all stars were lower luminosity, and we had stars of those low metallicity still forming today. We don't, because the interstellar medium is enriched in metals now. We don't form stars that low in metallicity anymore. But if we did, we'd have a whole main sequence that was just shifted to the left of where the main sequence is now. So that's the idea with luminosity class 6. Ready to explain that on the final exam? If not, you should ask me a question right now. Yes?
That first statement, N2 is lower. What's N2?
And this right here?
No,
Up there.
oh, it's NE.
It's NE, that's right, it's NE, yes. That's N sub E. Yes, N sub E. Yes?
Can you read what the statement on the right says?
Maybe. Did I write it clearly enough? So which one? Where at?
Like underneath subdwarfs.
Underneath subdwarfs. I'm just going to read the whole thing. Subdwarfs, luminosity class 6, have lower metal abundances. lower metal abundances, right? Lower metal abundances because they are old, and so God. And so the ISM had not, oh God. Ben, thank you for pointing this out. Enriched much when they were born. Oh, much better now. Yes. Yeah. Lower metal abundances. Yeah, you get a hamburger bun and it dances, right? A bun dances. Yeah, is that better now? Okay, good. Kind of hoping nobody copied that into their notes and it's just like, whatever, I guess this makes sense. I mean, I think Dr. Harmon speaks English, so maybe it's me. All right. Always proofread whatever you write. Yeah. Except when you're writing it in front of people. Okay. Blah, blah, blah. Okay. Let me get the projector on here. And I'll write something and then I'll show the image. So we talked about all these sources of line broadening. We have the natural width and on all these other sources of broadening, which tend to produce under stellar conditions larger contributions to the full width at half max or to the equivalent width than natural broadening does. And so I will point out that the total line profile which includes all these effects, all these sources of line broadening, is obtained by convolving the damping profile and the Doppler profile. And here's where I just have to say, okay, I could spend an entire class talking about what convolution is. It's a mathematical technique. How many of you are familiar with convolution integrals? So some of you have seen them before. Good. If you have not seen one before, too bad. I'm not going to do this now. The basic, I mean, not in any detail. The basic idea is like, and your phone uses this kind of thing. If you take a selfie and it uses bokeh, so it looks like there's a blurry background. With a small lens on a phone camera, the background's actually probably still in pretty good focus, but they're trying to make it look like it was taken by a camera with a larger lens, which produces a naturally blurry background because you have less of a pinhole camera effect. And so that emphasizes the subject, etc. Well, your phone computationally simulates a blurry background from a larger lens, and it actually does it in Fourier transform space, but it's equivalent to a convolution integral because what it does is it takes the point spread function, which is what the image of a point source would look like, and convolves it with the actual image. It takes the point spread function of a background that was blurrier, what an out of focus point of light would look like, and convolves it with the actual background to produce a simulation of the blurry background, because when you're taking a photograph in general, because of diffraction, a point source doesn't show up as a single point in your image. It shows up as something larger than that. And you can think of the image as made up of every point of light really creates a little point spread function. And it turns out you can use a convolution integral to represent all that. Anyway, again, I could make that a whole class. I don't want to. So you can just kind of, if that didn't make any sense to you, you can think of this as when you combine the effects of Doppler broadening and the natural line width, you get the Voigt profile. You can ignore the math, you can ignore the convolving part there. The damping profile and the Doppler profile, so the total line profile, and is called a Voigt profile. V-O-I-G-T, Voigt profile. Give you one guess as to the last name of the person who it's named after. Voigt problem. Oh, I'm on a roll here. Voigt profile. Okay. And so let's show it, shall we? Wake up. Come on, you can do it. There we go. Hooray. Now if I log in, it'll even be better. And if I give the right password, even better. Start. I hate it when that happens. Okay. There we go. Okay. Come on over there. And there it is. The structure of a spectral line. And so it's kind of a combination of the Doppler profile and the damping profile. And as I'd mentioned before, and I can't remember if there's a convoluted one here now. Let me look. Maybe not. Okay, yeah. So the idea is then it's a combination of two overall things. You got the Doppler profile, you got the damping profile, you got people watching at home who can't see this, so I go over here and turn the camera towards it. And so let's see, towards the line core, which one's broader, Doppler or damping? Towards the line core. The core is the middle part. Which is broader near the core, Doppler or damping?
Doppler.
Doppler broadening dominates in the core, but look at the wings. I'd mentioned before that the damping profile, it's narrower, but it falls off slower away from the core. And so away from the core of the line, in the wings, it's dominated by damping. So we say that spectral lines typically have Doppler cores and damping wings is the idea here when you combine everything together. So the Doppler profile dominates near lambda naught, the central wavelength. Stop that. No squeaking. None of this fingers on the chalkboard. The Doppler profile dominates near lambda naught due to its greater width. But because it falls off exponentially as opposed to the damping profile, the damping profile dominates far from the core. The damping profile dominates far from the core. And so we say that a line exhibits a Doppler core and damping wings. A Doppler core and damping wings. And again, there are folks whose a lot of their research can involve looking at the detailed structure of a spectral line and trying to infer details of the physics of the stellar atmosphere or whatever that is giving rise to those spectral lines. Questions, comments, observations? It's the last thing from chapter 9. We're going to move into chapter 10. Yes. Yes. It's going to be glorious. Okay. And the audience at home listened to me say all that without being able to see me write it. But, that's okay. I said it so clearly that they got it down anyway. But there it is. All that glorious gloriosity that I just wrote down. Okay, let's build stars, shall we? Or at least talk about how to build stars, give the ideas behind how you build stars in computers. We're going to predominantly talk about oh, can I erase this? Sorry. Can I erase this? Have people finished? What's that?
From me, yes.
Okay, anybody stopping me? It's too late anyway, but okay. So we're going to be talking about the equations of static stellar structure, where you assume that the star is not changing with time. And mention that real stars, of course, do change with time, and so we use time-dependent codes to study them. For example, MESA. Modules for experiments in stellar astrophysics. Probably not this semester, but next semester I'll have you play around with making some MESA models of stars. Some people I know are using MESA a lot in maybe their senior projects, but it's worth playing around with MESA to see some of what happens when you construct evolutionary models of stars. But anyway, Chapter 10, let's talk about, to begin with, this is stellar interiors now we're talking about, the equations of stellar structure, differential equations that can be integrated in order to make models of stars. So there's 4 fundamental equations of stellar structure that describe various aspects of the physics. And the first one is the equation that describes hydrostatic equilibrium. If we're talking about in a static star, if the star is evolving, then there's not a perfect equilibrium here, but we're talking about static stellar structure. So I'll put a thing here. Static is what we're concentrating on here because it's easier. Hydrostatic equilibrium, this describes the balance between the inward force of, you tell me, the inward force of gravity, the inward force of gravity, and the outward force of pressure. Yeah. And the outward force of pressure. Right? We've kept saying the words. Now let's put math behind all of this. And so what we do is we say, okay, for any little chunk of the star in equilibrium, the net gravitational force pulling it downwards has to be equal to the net pressure force pushing it upwards. And so let's draw a little cylinder of material inside the star. There's material everywhere. We're just drawing an imaginary cylinder that encloses some volume within the star. And we'll stick to kind of one dimension here. And so, in other words, we'll just worry about, and this is a good approximation for many stars, how things depend on radius, distance from the center. And so we will say that the bottom surface of my cylinder is at radius r, so to center of star. Way down there somewhere is the center of the star. The bottom of my cylinder is at radius r from the center. The top of my cylinder is at radius r plus dr from the center. So the height of my cylinder is a little distance dr, change in radius from the center between the bottom and top surfaces of my cylinder. And we'll say that its cross-sectional area, and therefore the area of its top face and bottom face, is capital A. And if we think about the pressure, I'll let people catch up with their lovely drawings of this. And I will tell you, by the way, keep this in mind as we're going here, as motivation to ask questions, should you have any, is I guarantee you, I'm going to ask you to derive the first 3 equations of static stellar structure on the final exam. I will want you to be able to just derive them just from the top of your head, basically. This one is the hardest of the 3 to derive from the top of your head, but it's quite entirely, eminently doable if you follow the logic here. So, pressure is pushing everywhere on the cylinder. On the walls, it's just going to balance out because you could always match some little patch on the left with some patch on the right, and the pressure forces will be equal and opposite on those 2 sides of it. So where the action is on the top and the bottom. For the top surface, is pressure producing a downward force on the cylinder or an upward force on the cylinder? On the top surface, is pressure producing a downward force or an upward force? Oh, yeah, the pressure will be pushing downwards on it. So I'm not talking about the gas in the cylinder, I'm talking about everything else, right? Because the cylinder can't exert a force on itself. Newton's third law, everything would cancel in pairs. So I'm looking at external forces on it. So yes, the gas in the cylinder itself is pushing up on its top surface, but I'm asking about outside stuff pushing on the cylinder itself. So the gas outside the cylinder pushing on its top surface is pushing downwards via pressure. So we say that there is a pressure force, and it's the pressure evaluated at r plus dr, because that's at a distance r plus dr from the center of the star. Now, P itself is not the pressure force. What is the pressure force? What do I do with the pressure? What do I have to do with the pressure to get the actual force on the cylinder? No, nothing as fancy as that. We'll assume the pressure is constant over the whole top of the cylinder because of the fact that it's all the same distance from the center. So yeah, multiply it by the area. Yeah, it's just, remember, pressure is force per unit area. So force per unit area times area is the pressure. Now, if the pressure were different from place to place, then yeah, I'd have to do an integral, PdA. But I don't need to do that because the pressure is constant. So therefore, P of r plus dr times A is the force on the top, which we'll note in a moment. Meanwhile, on the bottom, the external pressure P of r is pushing up. And the whole point here is that P of r plus dr must be less than P of r so that there will be a net upwards pressure force on it. So we're coming up with an equation which will tell us the rate of change of pressure with distance from the center in order that there be an upward pressure force on any little volume of the stellar fluid, as it were, the stellar plasma. So there's my picture. Pressure pushing down on the top, pressure pushing up on the bottom. Ah, stop that. Net pressure force. Net pressure force, we'll call it F sub P, will be minus A, the area, times P of R plus dr. Why is it a minus sign? Because it's pushing down, right? And R is increasing upwards. So it's minus A, P of R plus dr. And note, this is not P times the quantity R plus dr. This is the pressure evaluated at R plus dr, right? Pressure is a function of radius. So this is the pressure at R plus dr, okay? And then from the bottom, it's pushing up, so it's plus A times P of R. That's the net pressure force on my little cute cylinder of plasma. But then we realize, well, you know, if we want to sound scary, why, we could do a 2-term Taylor series expansion. Aww. Woo, right? And say that this will be minus A, but then in a moment I'm going to say, well, you should know, you don't even have to think of it as a Taylor series expansion here, that P of R plus dr should be P of R plus dP dr times dr. The pressure at R plus dr should be dP dr plus dP dr times dr minus P of R. So notice here I kept a minus sign out front, and so I have minus is plus A P of R for that last term there. And so we'll get to the conclusion, oh look, the P of R's cross out, and you're left with minus A dr times dP dr. The net pressure force is minus A dr dP dr. But if you have any doubts about the step that went from here to the next line, right? Is it not true that dP dr is equal to the limit as dr goes to 0 of P of R plus dr? Well, you tell me, what do I put on the numerator? Well, I said that part. P of R plus dr over dr. So dr doesn't have to be infinitesimal here. It could be just some finite little distance. What do I put on the top? The derivative, the change in the pressure divided by the change in the radius and the limit that the change in the radius goes to 0. What piece am I missing up here? P of R plus dr, then what? What's the change in the pressure between the top and the bottom? I'm literally asking for the pressure on top's P of R plus dr, the pressure on the bottom's P of R. What's the difference between those? It's P of R plus dr minus P of R, minus P of R, right? Minus P of R, minus P of R, right? So, okay, then we're going to take that limit eventually, but that's kind of a decoration here. We're just, as long as dr is really small, then we can say that, so if dr is very small, because we're taking the limit as it goes to 0, then we have that dP dr is equal to, that dP dr times dr is P of R plus dr minus P of R, right? The P of R plus dr minus P of R is just multiply through by dr, dP dr dr. Or in other words, this says that P of R plus dr is equal to P of R plus dP dr times dr, which was our second step right here. We replace P of r plus dr with P of r plus dp dr times dr. So it really just comes from, yeah, this is a two-term Taylor series. It's also just comes from the definition of the derivative, that delta p over delta r is a better and better approximation to the derivative as delta r goes to 0. And what's delta p? It's P of r plus delta r minus P of r. So it all is just the definition of the derivative that leads to that expression right there. And we are thinking in terms of dr being a small quantity here because we're trying to derive a differential equation here. So we're thinking of things in terms of if dr is very small, oh, but then we're going to take a limit and say that that's a derivative. What questions do you have? So if this is not something that's obvious to you, think about that. This is like super fundamental calculus here. You want to get to where you'd say P of r plus dr, oh yeah, that's obviously P of r plus dp dr delta dr, right? Pressure at radius r plus the rate of change of r with respect to radius times the little change in the radius will be the additional pressure going from P of r to P of r plus dr. That's just basic fundamental calculus. It's time for a break. If you like it better, by the way, another way to put this would be that dp dr is approximately change in p over change in radius, right? Delta p over delta r. So delta p is approximately dp dr times delta r, but this says that P of r plus dr minus P of r is approximately dp dr. If I just call delta r dr, it's the same thing that we were saying before. So if it's quicker for you to think in terms of dp dr is approximately delta p over delta r and go from there, that's another way to get this. Okay, so can I erase this part of it? Yes, I can erase this part of it. I'm doing it. Goodbye, you this part of it. All right. So, what does ADR represent? What does the cross-sectional area of the cylinder times its height represent? Geometrically, that is the cylinder's volume. That's the volume of the cylinder, right? That's the volume of the cylinder. Since ADR is the volume of the cylinder, since ADR is the volume of the cylinder, note that minus dpdr is the pressure force per unit volume in the fluid. Right? Because in other words, here's the pressure force divided by the volume. The pressure force per unit volume is minus dpdr. Minus dpdr is the pressure force per unit volume in the fluid. And note too that if dpdr were 0, if the pressure were constant, there would be no net force on our little cylinder because the pressure pushing down on the top would equal the pressure pushing up on the bottom. There'd be no net force. So there needs to be a pressure gradient in order for there to be an upward force on this. And the pressure needs to be decreasing the higher up you go, so that there's more force from pressure up on the bottom than from pressure down on the top, so that there'll be a net upwards force of pressure on it, because that upwards force of pressure has to balance its weight. It has to balance the weight of the fluid inside. That's this business of the balance between pressure and gravity, inwards gravity force and outwards pressure force. The outwards force of the pressure forces outwards because pressure decreases as you move away from the center. If it increased, it'd be the other direction, but then that wouldn't work. Okay. Yes?
What's the first, the second word?
ADR. Yeah, ADR, yes. Since A times DR is the volume of the cylinder. Yeah. Yeah, that's not ale or anything like that. Yep. Okay. What was I going to say next here? Oh, so if it's minus dPdR in our one-dimensional case, what would it be in the general case in 3 dimensions? How do you generalize like dPdR or dPdX to 3 dimensions as a vector? Because in general, force is a vector, right? So what would we do? Think vector calculus to generalize the idea of minus dPdR, because that could be just like one component in principle of the pressure force. If you had 3 components, right? One component could be like minus dPdX in the x hat direction. What would I do for the other pieces? I'd have minus dPdy times y hat, right? Minus dPdy times y hat. I mean, here it's r hat. We're in spherical coordinates, but let me just be in Cartesian coordinates for a minute. Minus dPdx x hat, minus dPdy y hat, minus dPdz z hat. What do you call that beast? What is the vector whose components are the 3 derivatives of some scalar with respect to the 3 coordinate directions there? That's the gradient, right? That's the gradient. So in general, the pressure force per unit volume is minus grad P. That's the general case. Or minus the gradient of the pressure in 3 dimensions, in the general case, I'll say. If pressure varies in all 3 directions, minus grad P, minus the gradient of the pressure, is the force per unit volume due to pressure. Okay, I'm going to keep my picture up because I want to be able to keep referring to it. So now we've handled pressure. Let's figure out the gravitational force. So if you're taking E and M, you know how to go from charge density and volume to the total charge inside of a little volume, right? That sort of idea. So we're going to do the same thing here, except I think Griffiths calls volume element d tau, if I'm not mistaken. We're going to be weird and call it dV. I know, isn't that weird? Who would imagine such a thing? The mass of fluid in the cylinder in its volume dV equals ADR is, we'll say that's dm as opposed to a little dq. So dm, in terms of the mass density and the little volume, dm is what times what? What do I do here? I even said times. What do I do with density and volume to get mass? So just take the density times the volume, right? So dm is rho dv. Rho dv, just like dq is rho d tau in Griffiths, right? If you're thinking in m, but this is mass density instead of charge density. So it's rho ADR. dm is rho ADR. So the downward gravitational force on it is F sub g is equal to minus rho times g, the local acceleration due to gravity, times ADR, right? The force of gravity is minus dm times g. Minus because it's pointing downwards, that's what the minus sign says. And dm is rho ADR. Maybe I'll put a little thing in between just to emphasize, in case you're looking back later and like, wait, what? It's minus dm times the local acceleration due to gravity, so it's minus rho a g dr. G is the local acceleration due to gravity, not 9.8 meters per second squared at some arbitrary location inside of our star. How do you get the gravitational acceleration? Well, all the mass of the star behaves as though it was located at the center, except that we have to only include mass which is interior to our radius. So in other words, do you remember from your E and M, if you have a spherical ball of charge and you're somewhere inside of it, only the charge interior to your radius contributes to the force at your location. Gravity, just like the electrostatic force, is an inverse square law force, and that's what gives rise to that fact that only the charge interior to your radius counts. And so the same thing happens with gravity. Only the mass interior to your radius produces a net gravitational force on you. And so if we are at some location within the star, at radius r from the center, we can say that m sub r is the mass interior to radius r. M sub r is mass interior to radius r. The mass interior to radius r. And if I had a little dm right there, my little volume of fluid right there of mass dm, then the force of gravity on it is equal to what? What does Newton's law of gravity say? It says it's equal to minus big G times what over what?
M1 times M2 over R squared.
Right, M1 times M2 over R squared. So what are playing the role of M1 and M2 in this case? MR and dm, right. M sub r is attracting dm towards the center gravitationally, so it's minus g m sub r times dm divided by r squared, where r is your distance from the center. So the gravitational force on our little cylinder is minus g m sub r dm over r squared. In other words, remember that gm over r squared is the local acceleration due to gravity. That's the g that showed up over there, right? Just like what is the local acceleration due to gravity on Earth's surface? It's minus, well, it's ignoring the minus sign, g times the mass of the Earth times the radius over the radius of the Earth squared is what gives you 9.8 meters per second squared. G mass of Earth over radius of Earth squared is 9.8 meters per second squared. But in our star, it's only a coincidence that that's 9.8 meters per second squared somewhere. In fact, it's not. The sun's surface gravity is much stronger than that. So please don't think that G is always 9.8 meters per second. A little pet peeve of mine is when people say gravity, meaning the acceleration due to gravity. No, that's not gravity. That's the acceleration due to gravity at some location. That's not gravity. Stop saying gravity is 9.8 meters. Stop it! Okay, so anyway. You can tell I feel strongly about this. So this will be minus rho times g m sub r over r squared times ADR. that is the gravitational force on our little cylinder, where again, m sub r is mass interior to radius r. Yes?
You drew a circle there. Can you show how we're relating back to the cylinder?
So none of this has to do with that. So, and I didn't label it, but this could be like the radius of the whole star, right? Oh, this little circle here, is that what you mean? Or
Cylinder and the big diagram.
this one right here?
Yes.
So our little cylinder is here. Whoop. Right, I'm making it much too large. There's our little cylinder, right? Whose axis should be toward, the axis is along the direction to the center of the star.
I understand.
Yeah, any little cylinder I could draw, that's what we're dealing with there. Yes. Uh-huh. Yep. Okay. So now we just apply Newton's second law to our cylinder. Newton's second law applied to our cylinder says that the mass of the cylinder times its acceleration, right? So dm, I'll first write it as dm times d squared r dt squared, right? Because it's moving, it might be accelerating in the r direction, so d squared r dt squared is the acceleration. Mass times acceleration is equal to the sum of the forces. It's equal to the gravitational force plus the pressure force. It's their algebraic sum. You have a minus in there, but their algebraic sum is Fg plus Fp. But dm is equal to what again? What do I replace dm with in terms of rho and a and dr? What's that? Yep, rho a dr, right? So we have that rho a dr d squared r dt squared is equal to the gravitational force minus rho g m of r over r squared adr minus rho g m of r over r squared adr. And then before we said that the net pressure force was minus dpdr times adr. And oh, look at that, there's ADRs in every term that just drop out. So we get to cross out ADR in every term. Lovely, it cancels out. Which is better, because it shouldn't depend on how big you made your cylinder or anything like that. This is just be this general equation. So what we get is, gloriously enough, rho d squared r dt squared is equal to minus g m sub r rho over r squared minus dp dr. Ta-da! That's Newton's second law applied to our little cylinder, which is saying that its mass times its acceleration is the sum of the upwards pressure force, because dpdr will be negative, so the minus dpdr is positive because p is decreasing with height. So as r increases, p decreases, so this dpdr itself is negative. So minus dpdr is the upward pressure force. Add that to the downward gravity force, and that's per unit volume, the mass times the acceleration of the cylinder. Because notice, rho is per unit volume, dpdr is pressure force per unit volume, this is the gravitational force per unit volume, and this is the mass per unit volume times the acceleration. So implicitly, everything is per unit volume here, because we divided through by the volume. So in a stellar evolution code in general, where the star can be changing with time, you want some version of this equation, because it's telling you how things can move in response to disequilibrium between pressure and gravity. But we want static models, so we get to say that d squared rdt squared is 0, that pressure and gravity are in balance. So in hydrostatic equilibrium, pressure and gravity in balance. In hydrostatic equilibrium, d squared rdt squared is equal to 0. If our star is static, neither expanding nor contracting, d squared rdt squared is equal to 0. And so we get that dpdr is equal to minus g m sub r rho over r squared. Yeah, there you go. And that's so important that it is hereby equation 1 with a circle around it, so we can keep referring to it later. Or if we like, we can say dpdr is equal to minus rho g, where g again is that local gravitational acceleration. And again, keep in mind what this means. This is talking about the magnitude of the pressure force. Well, sorry, I shouldn't say that. The minus sign means something. That pressure and gravity are in balance with one another. That the upward pressure force is in balance with the downward gravitational force. And, you know, again, I'll want you to derive this on the exam. I will provide you with that diagram, which this duplicates a figure in the book. I'll provide you with that and then say, refer to this in order to derive dpdr is minus gm of r rho over r squared. Okay? So that's your cue to where if you have any questions, ask me. And it's also your cue to look over this carefully later and get to where it just becomes intuitive, because, you know, it took us a while and it might sound complicated, but fundamentally it's not complicated if you follow through the logic on everything. Should dpdr equal minus rho g in this room? Yeah, it does, because in our atmosphere, any little chunk of atmosphere, here's this little chunk of atmosphere of air. Does it weigh something? Does it have mass? So is it pulled on by Earth's gravity? So it weighs something. If that was the only force on it, what would it do? It would fall to the floor. Is it doing that? No. So something must be balancing that gravitational force on it. What's balancing the gravitational force on it? The fact that the pressure down here is a little lower than the pressure up here, so that there's a net upwards pressure force. So yes, this applies in this room. The pressure at the ceiling, the air pressure at the ceiling is a little lower than the air pressure on the floor because of the need for pressure to balance gravity. Meanwhile, gee, if you climb a mountain, tell me, does it become harder to breathe enough oxygen or easier to breathe enough oxygen? Becomes harder because the air is quote unquote thinner up there, right? Ta-da, right? In other words, because pressure needs to decrease with altitude in order for there to be in any layer of the atmosphere, or any little chunk of it, as much upward pressure force as there is downward gravitational force. This is why air is thinner on the mountaintop. It's because the air pressure needs to decrease in order for there to be equilibrium. Now, a complication, and this happens in stars too, in their convective zones, is that in the troposphere of the Earth, we have convection. And so that means that there are blobs where they're buoyant, and so the pressure force is bigger than the gravitational force. Those same blobs rise and then they sink back down. They get to be where they're denser than average and the gravity is stronger than the pressure, but still in an average sense, even within the Earth's so-called troposphere where it's convective, in the average sense, pressure and gravity are described as in balance with that equation right there. So it's everywhere. This is part of your life, even if you never thought about it before. So, okay, what questions do you have? So that was the hardest of these first three equations. Now, the fourth equation that describes energy transport, that's going to be like a whole class right there. That one gets more complicated. But we're going to do the next two equations, and it's going to be like, they're very simple. Did that actually brighten when I snapped my fingers? Wow, I have such power to make blue get brighter. What's that? Yeah, yeah. What is it? Clap on, clap off, clap on, clap off, the clapper. Oh my gosh, it worked! Amazing, it's a miracle. Yeah, right, clap on. There we go. Wow. You know what? You're a one sharp student. I mean, I guess that could be the point. Maybe my jokes would go over like a lead balloon. I'll be here all night. All right. Now, our next equation is the equation that describes mass continuity. Mass continuity. You could also think of it as like mass conservation. On some level, it seems really obvious, but if you think about it, you still have to have an equation for it. You still have to tell your computer, if you're numerically integrating these equations, you still have to tell it this. It's still a condition we need to impose. And so again, you've seen this in E&M too. We're just generalizing to mass. So consider we're within the star. And so here is a shell at whose radius is inner radius is r, and its thickness is dr. So its radius is r, its thickness is dr, and inside that shell is a little mass dm sub r, which is the additional mass interior to radius that you get by moving from r to r plus dr. So in other words, dmr there is the mass interior to radius r plus dr minus the mass interior to radius r. It's just how much mass is in that little thin shell. And again, this would really be in the limit as dr goes to 0, right? It's the usual kind of calculus limits kind of stuff. Is the mass contained in the spherical shell. So m sub r is how much mass is interior to radius r. M sub r plus dr is how much mass is interior to radius r plus dr. And so dmr is the difference between those. It's how much mass is inside the shell itself. And if this was a ball of charge with charge density rho, as a function of radius. It doesn't have to be constant. And you had a thin spherical shell. How much charge is in that shell? You've probably done this in E&M. Is that true or not true? Have a little thin spherical shell. The local density is rho as a function of r. What's dq? What's the charge in that little shell? Well, it'll be the density times the volume, right? So what we need is the volume of that spherical shell, right? Volume of spherical shell is dV, or d tau if you want to be Griffithy about it. dV is, what's the volume of that little shell? Okay, yeah, it's 4/3 pi r plus dr cubed minus 4/3 pi r cubed, but blah. What is the, thinking of it as a thin shell, right? When you make these like integrations that you do, what is the d tau, the dV of that little shell? Oh, crickets. Oh, that's it. I'm telling Dr. Trees. If somebody doesn't stop me by telling me what that volume is, I'm going to go tell Dr. Trees nobody knew how to do this. Are you going to stop me? Times. Because 4 pi r squared is the area of that inner sphere, right? But then what do I need to do to turn that area into a volume? Oh my God, no. Times dr. Oh, whoa, just in time, right? Area times thickness is its volume. In the limit that dr goes to 0, right? It's an approximation, but in the limit that dr goes to 0, its volume is 4 pi r squared dr, right? So you do know what will happen if you integrate that from 0 to capital R, right? What will happen? If I want the whole volume of the sphere, let's see if this is dawned on you. The whole volume of the sphere, I add up all the little dVs, so I integrate from, if the whole sphere has radius capital R, then I integrate from 0 to capital R of all the little dVs, 4 pi r squared dr. What's the integral of r squared? R cubed over 3, so I get 4/3 pi r cubed evaluated between 0 and capital R, which is 4/3 pi r cubed. Does that look familiar for the volume of a sphere? You get it from integrating dV, right? So, okay. dV is 4 pi r squared dr. And so what's dm of r? What's dmr? If dV is 4 pi r squared dr, what do I multiply that by to get how much mass is in the little shell? What do we describe to say how much mass there is in every little unit volume? Well, that's what I'm looking for, but in other words, what property of the gas or liquid or whatever, or solid, whatever it is, what property of it do I need to know to get that little dm there? Yeah, it's density, right? Yeah, it's density. So dm sub r is 4 pi r squared rho dr. And so therefore, we get a differential equation, which is the one we're looking for, that the derivative of the mass with respect, the mass interior to radius r, with respect to r, dm sub r dr, is 4 pi r squared rho. Ta-da! And really then that's very simple, right? In other words, you just need to realize, well, dmr is mass times volume. Density times volume, and the volume's 4 pi r squared dr, and we're calling the density rho as a function of r. It's implicit rho could be a function of r here. So 4 pi r squared rho dr is the little mass. Divide through by dr, dm sub r dr is 4 pi r squared rho. That is the equation of mass continuity that gets the designation. That's equation number 2. That's the second equation of static stellar structure. So we've got 2 differential equations so far, one for dPdr, one for dm sub r dr. And again, this one just drops right out, right? Nothing too complicated about this one, I hope. Okay, questions, comments, observations? A comment could be, wow, this is so cool.
Wow, this is so
Yeah, I agree. I absolutely agree with you on that. Okay, the next one is the equation of energy generation. Which is just going to have this thing in it that just says, this summarizes all the complicated physics. We're going to say, because to calculate this, it's like, okay, let's do some nuclear physics. But to just say there is this thing that must represent how much energy is being generated per second per unit volume, well, that's not complicated at all. So energy generation. Energy generation. We're going to let epsilon, which will be the sum of epsilon nuclear, energy generated by nuclear reactions, so that would get complicated to actually calculate it. Lots of details hidden in there, plus epsilon gravity, because stars can also have gravity power. If they shrink, they're converting gravitational potential energy into thermal energy and radiation. And if they expand, it's the other way around. So, and you know, did we ever talk about, like, if a star were slowly shrinking, it would be converting gravitational potential energy into thermal energy and radiation, and then we'd describe it with the theorem, the virial theorem, right? So we know already that you can have something be gravity powered. You can convert gravitational potential energy into other forms. So those would be the 2 sources of energy the star could have. A protostar is gravity powered. A full-blown adult star, so to speak, is generally nuclear powered. But a supernova explosion, that's gravity powered, almost entirely gravity powered, because the iron core of the star collapses in almost an instant into a ball of neutrons, and that's a huge release of gravitational potential energy that happens there. So almost all the energy that comes out of a supernova is from gravity, not from nuclear power. And in fact, people might at first guess, well, nuclear energy is probably a bigger source of energy than gravity. And no, actually, when gravity is a source of energy, it tends to really dominate. Like accretion disks around black holes, that's gravity power. And it can just be astounding how much you can get out of that. But anyway, epsilon nuclear plus epsilon gravity, let that be the energy generated per kilogram in a spherical shell. I mean, it doesn't have to be in a spherical shell, but we're making one-dimensional models. They only depend on radius. So we're thinking in terms of spherical shells. Let epsilon be the energy generated per kilogram per second. My notes don't mention the per second part, so I should really say the power generated per kilogram in a spherical shell. The energy generated in the shell contributes, finish writing it. The energy generated in the shell contributes dL sub r, capital L sub r, so I'm introducing a new concept here, contributes d capital L sub r to L sub r, which is the luminosity emerging from the outer surface of the shell. So, big picture here. Okay, I'm going to cheat by just erasing that M and making it an L. So I encourage you to redraw this picture with an L there instead of an M. It's the same picture, but with a capital L instead of a capital M. So L sub r equals the what do I want to say? It's what I said over there. It's the luminosity. It's the total power emitted, total power radiated outwards from a surface of radius r centered on the center. In other words, it's at distance r from the center. From a surface, a distance r from the center. I'll put it that way. Now we know in the sun, the energy is generated in the core. There's thermonuclear energy being generated in the core. And so if I'm outside the core, if I'm outside the core, I could talk about, here is, well, actually, this doesn't even have to be a thin shell. So I'm outside the core, and here's a surface of radius r1. Pretend that's an actual nice circle or sphere centered on the core, on the center. Your drawing will be better than mine, maybe. Oh, God. Okay, pretend those are beautiful, perfect circles making lovely spheres. Use your mind. Okay, radius r1, radius r2. So if we're outside the core, how should the luminosity, the net power flowing out of surface with radius r2 compared to that flowing out of the surface with radius r1? How should L sub r2 compare to L sub r1? So if L sub r2 were greater than L sub r1, would it not be the case that that would mean that more energy was leaving the volume between them than was entering it? Because energy is leaving through the outer surface and entering through the inner surface. So if those two were not equal to one another, there would be energy building up in this volume between those two radii. Does that make sense? Okay. So could that be an equilibrium situation? Is that sustainable? Could that just last forever? Because equilibrium means the conditions are not changing over time. So if we're in equilibrium, could there be a net flow of energy into or out of this shell right here, this thick shell? No, there could not. In equilibrium, there can't be energy building up or diminishing it within it. So given that, I ask the question again, how does L sub R2 and L sub R1 compare? How do they compare to one another? They're equal to one another. They have to be equal to one another if we're outside the energy generating region of the star, the core. Those two quantities have to be equal to one another. But when we're in the core, now we're talking about, so here, let's say we're inside the core now, inside the energy generating region, now there's energy generated. Well, I'll say power, because we're really talking per unit time. So power generated in shell how can I get that? So if epsilon is the total power per kilogram, power per unit mass generated in this shell, we're calling that dL sub r. dL sub r is the power generated within that little shell of thickness dr. Epsilon is the energy generated per kilogram by either nuclear reactions or gravity or both. So how do I go from epsilon to dL sub r? What property of the shell takes me from power per kilogram to power generated within the shell? What do I multiply the power per kilogram by to get the power generated within the shell? The number of kilograms in the shell, also known as dm, because we're calling dm the mass of the shell, right? So dLr is going to be dm times epsilon, Well, if only we had an expression for what dm is in terms of, say, the radius and dr. What might, and maybe the density. What's dm? dm is it's that whole 4 pi r squared rho dr, right? Volume of the shell times its density. So this is going to be 4 pi r squared rho epsilon times dr. 4 pi r squared rho epsilon times dr, because 4 pi r squared rho dr is the mass of the shell. So in other words, what we find is that dL sub r dr is equal to 4 pi r squared rho epsilon, and that is equation 3, and notice how similar it is to the equation of mass continuity. Why, they're almost twinsies. They're almost twinsies because all we have to do to get from the equation of mass continuity to the equation of energy generation is multiply through by epsilon. Multiply through by epsilon. And here I said d little m, and I wasn't thinking, because that's fine, but it's better to think of it as dm sub r, because that's what we're calling the mass of the little shell. So dm sub r times epsilon is how much luminosity is being generated in the shell. So this equation is literally equation 2 multiplied through by epsilon. It literally is that, because epsilon times dm is dLr. So it's literally just multiply through by the energy generation rate to get the the equation of energy generation. And if we're inside the core, right, then the idea now is if I have, what's that? Almost perfect, yes. I mean, not perfect, not down to the micron, but not too bad, right? Then here's R plus dr, right? And then the idea is that L sub R emerges from inner surface and L sub R plus dr emerges from outer surface and this time they're not equal because we got some energy generated within that shell that's incrementing how much radiation is flowing out of the outer surface. L of R plus dr minus L of R is that dL sub R, that extra luminosity that is coming from the shell. So if you're in an energy generating region, the luminosity increases with distance from the center. More and more of the luminosity is coming out of radii further and further from the center. And then once you're out of the energy generating region, then L of R is constant. L of R stays constant if there's no energy generation because there has to be just as much energy flowing out of every of every shell as is flowing into it. But in the core, then that's not true anymore because you're actually generating energy, and so as you move out, you're adding more and more luminosity as you go. What questions do you have? So this is good stuff to be thinking about. Think about how all this works because this is fundamentally how we construct models of stars. This is the first step, is thinking in terms of things like this. And again, if you're not in equilibrium, well then it becomes more complicated, but still the principles in general are the same. And this is, this kind of thinking is how you construct differential equations to represent physical phenomena. You imagine little regions and little dRs and dMs and stuff like that. This is how you construct differential equations that describe physical systems. It's this kind of thinking. Okay.
How does the star hold itself if it's not in equilibrium?
Well, it'll be changing with time, is what it comes down to. So if it's not in equilibrium, for example, when the sun runs out of central hydrogen, it'll start fusing in a shell surrounding the core. And that'll be much more rapid than is happening in the core now because of the high temperature. And so the sun's outer layers will not in fact be in equilibrium. The flood of energy from the hydrogen fusing shell will cause pressure to exceed gravity in the star's outer layers, which is why it swells up to become a red giant and why it's growing the entire time. In other words, it doesn't become a red giant and then it's just sitting there. No, the whole time it's expanding because it's not in equilibrium, because pressure is stronger than gravity in the outer layers, and so it swells up as a result of that.
And then eventually the outer layers are no more bound by the gravity.
So that's why you can get stellar winds like that, because if you get the outer layers far enough away from the center, then gravity gets very weak out there and the radiation pressure can start to be enough to blow the outer layers of the star off, which is why the sun, in the end, because of that and because of helium shell flashes, it'll lose about half its mass before it becomes a white dwarf. The sun's white dwarf will only be about half the mass of the sun because it'll have lost half of its mass from combination of stellar winds and the helium shell flashes, that blow off the outer layer. Yep. Yep. So yeah, please don't get the impression I'm saying stars are always in equilibrium. They are not. But for large portions of their life, they're pretty close. but only close. The sun's core has a little bit more pressure than gravity. It's shrinking very slowly and heating up. The sun, as a result, is the nuclear reactions are going faster. The sun was only about 60% of its current luminosity when it was on the ZAMS, the zero-age main sequence. And it's slowly brightening even as we speak. Now, in our lifetime, that's not going to have much of a consequence, but in about 500 million to a billion years or so, it's going to drive the Earth into a runaway greenhouse effect. The Earth will turn into Venus long before the sun turns into a red giant. It'll happen while it's still on the main sequence. Unless we build a giant parasol to block some of the light, which we could actually do. We could actually intervene and build a big parasol at the L1 Lagrangian point between the Earth and the sun and block some of its luminosity and keep ourselves safe. And then finally, humanity or our distant descendants would have a positive impact on the biosphere. So there you go, something to look forward to.
Indeed.
Yes,